Let's take a look at a few examples from the homework on 4.5 and 4.6. Keep in mind that, especially in 4.5, not everything's about column space, null space, row space. It could be any old vector space. All vector spaces have dimensions. So one of the things they do in 4.5 is describe vector spaces any old way they can think of. So particularly in 1 through 8, they say find a basis for this subspace and also state the dimension. So in number 2, they say, hey, just any R3 vector that has this particular format. And I'm going to take a little bit of time to rewrite that format. There's a choice of A and a choice of B. There's basically two free variables. So I'm going to rewrite this as 2A 0, negative 2a plus 0, negative 4b 0. I was just breaking it up into the a's and the b's because those are my free variables here. And if you really need to drive the point home, you can say this is 2, 0, negative 2 times a plus 0, negative 4, 0 times b. So it really is it's the span of these two vectors, all linear combinations of these two vectors, which means that these two vectors are a basis for the subspace. And obviously the dimension of the subspace is 2, because there's two basis vectors. So you can do the same thing with number 4. Maybe I'll condense my process here a little bit. The p's are 1, negative 1, 3, 1. And the q's are 2, 0, negative 1, 1. So again, the dimension of that subspace is also 2. And there's your two basis vectors. If you look at number 3, with 3 free variables, I bet you can figure out what the dimension of that's going to be. And with a little work, you can write down the basis vectors. Okay. Moving on to number 10, it says find the dimension of the subspace of R2 that is spanned by these 3 R2 vectors. Keep in mind the biggest that any dimension can be for an R2 subspace is 2. Right? 2 linearly independent vectors is the most you can have in R2. And normally we would just slap these into a 2x3 matrix and row reduce and see how many pivots we've got. However, because keep in mind span is the same thing as column space, really, once you put these into a matrix. However, looking at these, I just happen to notice that negative 210 is negative 2 times the first one, and this is negative 3 times the first one. They're all multiples of each other. So I can see that all 3 of them are, well, 2 of them are linearly dependent on the third one. There's only one linearly independent vector here. So this just has a dimension of 1. I can just see that by inspection. However, if you didn't happen to notice that, you would still put these into a 2x3 matrix, and when you do row reducing, you can probably just see right away here that 5 times the first row makes the second row. So when you row reduce, you'll only have one pivot, which means that there's only a dimension of 1 again. Okay. So the same thing is true, the same instructions here for 11 and 12. Again, for 12, I can see that these are R3 vectors. There's 4 of them, so at least one of them is dependent. It's not so obvious to me this time. I guess I can, no, they're not multiples of each other. It's not so obvious to me if there are 3 linearly independent ones here. So I will just have to stick this into a 3x4 matrix and row reduce and see how many pivots I end up with. Okay, so I just wanted to make you aware of some of the types of things they're going to throw at you in 4.5. Let's go ahead and look at some of the 4.6 questions as well, where we're talking about rank. So one of the things they'll do is similar to the example I had in the last video, where they give you a big old matrix, but they give you the reduced version as well, or at least a row equivalent version. It's not fully RREF, it's just REF. But really that's all we need, because we can see the pivots from that. So they want, without calculations, list the rank of A, which again, keep in mind is the dimension both of the column space and the row space. So they want the rank of A and also the dimension of the null space of A. Then they want bases for all three of those. So first of all, let's go through and just pick out the pivots. So there's one there, one there, one there, one there, and one there. So there are a whopping 5 pivots here. Which means the rank of A is 5. And since there are 1, 2, 3, 4, 5, 6 columns, that means the dimension of the null space of A, there's only going to be one free variable, and so the dimension of the null space is 1. Bases for the column space are going to be 1, 2, 3, not that one, 4, 5 columns of A. Has to be of A for the basis for the column space. The basis for the row space is going to be every row that has a pivot. And that could be the rows of A or the rows of B. Either one of those works for the basis for the row space. So I'll just say those 5 rows be basis for the row space. Notice the row space is R6. The column space is R5. The null space is also going to be R6. It's going to tell you how to combine the 6 columns to make a 0 result. So we've got, I sort of arrowed out here the bases for the column space, the row space. The basis for the null space is going to take more work. That you'll have to write down the x6 equals 0, x5 equals x6, and so I do all that stuff. A little bit more work, but you'll be able to get it. Then you get some of these, there's only a few of these with numbers and matrices. You get these conceptual questions after that, starting with, I think, with number 6. And they're all a little bit different. I just wanted to point out a couple of them just so you're not tripped up by the whole idea of it. So 6 says, suppose you've got a 7 by 5, and keep in mind, again, that's rows by columns. So 7 rows, 5 columns, has a rank of 2. So rank means that there were 2 pivots. So it has a rank of 2, so what's the dimension of the row space? Well, here, let's back up. Dimension of the null space, first of all. So if there's 2 pivots on your 7 by 5, that means there were 3 more columns that did not have pivots. So dimension null space, we know the dimension of the null space plus the rank has to equal number of columns. So dimension of the null space is 3. Dimension of the row space is the same as the dimension of the column space, is the same as the rank, is 2. So they're just checking to make sure you know your stuff here. And that should be a give me question. But the dimension of the row space is the same as the rank. It's 2. They also want the rank of the transpose. So if you took your 7 by 5, turned it into a 5 by 7, Then the rank of the transpose. So the rank of A transpose, which is now a 5 by 7. And those two pivots that were pivots in rows now become the 2 pivots that are in columns. And the rank of the transpose is still those 2 pivots. Since the pivots work for the rows and the columns, when you flip rows for columns, you still just got 2 pivots. So the rank of A transpose is still 2. So that's the sort of thing you're getting in these questions. 8 says it a slightly different way. You've got a 6 by 8 matrix that has 4 pivot columns. That's essentially the same thing as saying the rank is 4. What's the dimension of the null space? So it's a 6 by 8. There were 4 pivot columns, so 4 free variables. Is the column space equal to all of R4? And it seems like you've got 4 pivot columns, you've got 4 linearly independent columns. It should be all of R4, except what are the columns? Are they R4 vectors? And they are not. This is a 6 by 8. There's 6 rows, so each column has 6 entries in it. So the column space is not equal to R4. And it's also not equal to R6 because there's only 4. You need 6 vectors to span all of R6. So, like I said, each one's a thought question. Each one is a little bit different. But you, where's my camera? You right there. You are super smart. You will figure all of these out. I have full confidence in you. I'm so proud of you. You can do this.